So now we will talk about multi-carrier modulation. So simple form of multi-carrier modulation divides the data stream into multiple substreams to be transmitted over different orthogonal subchannels centered at different subcarrier frequencies. So what does that mean? Say we have a channel. So as I was telling you, if at all you have a signal HFN and you have a channel HFN which is corrupting your signal, and say you get an output. If at all you want to able to recover XFN from YFN, you need to estimate a channel, and you want this channel response HFF, right? Because you want to do, say, frequency domain equalization. You want this HFF to be a constant. That means you want it to be a flat number, right? You do not want these kind of variations. Okay, so you can see here in this particular channel, for example, the channel response is such that over a large bandwidth, different frequencies, you can see some frequencies experience a very less attenuation, whereas some frequencies experience extreme attenuation. So the task is, if at all you try to avoid, okay, so in this particular situation, by the way, is called as a frequency selective fading. Different frequencies experiencing different amount of fading, and how you are going to tackle this particular thing. So as I told you, so it is closely related to time delay spread. So what you are supposed to do is, say your time delay spread is say 1 millisecond, then you are supposed to have the bit duration at least 5 times more than the time delay spread, or 1 by time delay spread is called as coherence bandwidth. So you divide the entire bandwidth with so many smaller pieces, right? Say I divide this B into 10 pieces, then B divided by 10. You break them into so many smaller pieces such that the individual bandwidth is much smaller than the coherence bandwidth. Okay, so that's how we tackle fading. I think we have discussed this in earlier class. So that's what it's all about. So how we are going to do this particular thing? So how this is going to happen? Sorry for that glitch here. Okay, here we are. So how would you do this? Okay, so typically the idea would have been you take your data, convert the data from serial to parallel, and then afterwards individual data. Now when you convert the data from serial to parallel, suppose there are 100 bits. If at all you are sending 100 bits, say in 10 seconds, then what you can do is you can convert them. Convert that 100 bits into 10 streams of 10 bits each. Okay, so then what's going to happen is this entire speed, whatever you are going to have, is going to be reduced by a factor 10, but then you need 10 parallel channels, fine, but then each of those data, slower data, whichever you are talking about now, needs individual local oscillators for modulating them. Okay, that's a symbolic one. And how it is done cleverly, by the way, is you have a better method of doing it. So the idea is of implementation of a multi-carrier modulation is what you do is the same thing is done by this tool called as IFFT, right? So what does an IFFT or an FFT do? So as a student of digital signal processing, we all have studied. So the task of DFT is to break a signal into its different frequency components, right? That's what we have been studying. And second thing we studied was each of those frequency components would be orthogonal to each other. Remember those basis functions, x of k equal to x of n e to the power minus j 2 pi by n into kn. You remember those w's, the basis functions, they were all orthogonal to each other. I hope you remember. So what people thought, instead of having this old school method, so why not apply fast Fourier transform? And it worked. So what FFT does is you take some data, say you take a data and you take 8-point DFT, then the entire data will be broken into 8 subcarriers. So if at all this entire thing, okay, so each of these lobes here, by the way, each of these lobes here, they are called as subcarriers. This entire thing will be called as a carrier. Now each of these are called as subcarriers. If at all you take an n-point DFT, there will be n number of carriers from 0 to n minus 1. By the way, we are showing an overlap here. Did you see we are showing an overlap? So this is indicating that it's not a good thing, by the way. We have been telling you aliasing and all this stuff. Overlapping is not good. But if the carriers, the subcarriers are orthogonal to each other, orthogonal in the sense, if at all you use the same carrier frequency, you recover the data. Use a different carrier frequency, the data, suppose I use a carrier frequency F2, then the value at F1 will be straight away eliminated, or value at F0 will be straight away eliminated. So recovery is easy. So what you do is, if at all you want to convert the data into several low frequency substreams of the data, what you do is you simply apply a DFT, and that should be fine. Okay. So this is a typical implementation of a multi-carrier modulation. Here on, we will be calling this as orthogonal frequency division multiplexing. So why the name orthogonal? See, because you are converting them into several multi-carriers, fine, but all those multi-carriers, F0, F1, F2, they are all orthogonal to each other. So orthogonal frequency division multiplexing. So how is the block? So you have your modulation, whether you want to use BPSK, QPSK, or COM. So the trending one is COM. So COM, convert the data from serial to parallel, right? So now you do not have any freedom because you want to take a FFT, right? So it has to be a radix 2, right? Radix 2 or radix 3. So you cannot get a 27 point or a 31 point. You have to go for 2, 8, 16, 32, and so on. So that may, okay. So this R bits per second will be broken down into R divided by N. That will be the new speed. Then afterwards, IFFT. Now, why not FFT? Why IFFT? Let me tell you one thing here. Why not DFT? Why FFT? So the concept was there of multi-carrier modulation earlier. It was the FFT, the ability to do it faster, that made the whole revolution possible. Otherwise, it was earlier, it was there only in some research journals. It did not make into commercial deployment. So it is the FFT which has enabled this whole LTE, I should say. Okay, so here we are IFFT. Why IFFT? We usually have the habit of taking the data. In IFFT, the input is supposed to be frequency and output is supposed to be time. Now, since here you can see we took our data, we reduced the speed. Okay, we took our data and we reduced the speed by converting it from serial to parallel, and then we are putting it on a time domain channel. Okay, that means input is reduced. The speed has been reduced. That means frequency has been reduced, and finally, to be able to put the data on a time varying thing, that is on a channel. So symbolically, they use IFFT. Even you use an FFT at the transmitter and IFFT, it will still work, but IFFT is the preferred one to avoid any confusion. So you take your data. Then afterward, there is a trick thing called as adding cyclic prefix. We will discuss the cyclic prefix. Then converted data. You converted the data from serial to parallel. Then you convert the data back from parallel to serial. You convert it into suitable analog data and take a center carrier and you just modulate it. Okay, you take a center carrier and just modulate it, and there you go. Okay, so you have your orthogonal frequency division multiplexing. So what do you do at the receiver side, by the way? You can see this is the transmitter. You took IFFT. At the receiver, you take FFT. At the transmitter, you add a cyclic prefix. At receiver, you remove the cyclic prefix. So here, transmitter, you had a digital to analog converter. At receiver, you have an analog to digital converter. Okay, so same carriers at both the ends. Okay, so that's OFDM transmitter and receiver with IFFT at the transmitter, FFT at the receiver. Okay, so now a few things that are troubling us is why cyclic prefix. So now let us talk about cyclic prefix. We have a little thing involved in cyclic prefix. What we want to be able to do is, let us see this particular channel first. Okay, so here are certain basics. So first thing to say is you have your OFDM symbols, several OFDM symbols being put. You tend to keep some guard band in between. You tend to keep some guard time in between. Why? Because there is likely possibility of a time delay spread. Even though you have slowed the data, but there is a chance of a time delay spread. So it is advised that you keep certain gap in between. Okay, it is advised to keep certain guard time in between. That is one thing. The second thing is, what are you visualizing your channel as? What are you visualizing your channel as? Now, what you have done already is you have taken the pain of taking IFFT at the transmitter, and at the receiver you are taking an FFT, right? So when you take an FFT at the receiver, so what are you receiving at the receiver, by the way? You are receiving a Y of N, right? So you had this nice data X of N, but in the channel, what has happened is the data has gone back due to the activities of the channel, and what you have received is Y of N. Fine. And then, now what is the advantage of you doing an FFT at the receiver? What you can do possibly is, if at all you have the channel estimated sufficiently, right? Channel estimation is a routine process. So given the knowledge that you know the channel, okay, which is called as channel estimation, the channel response. And so however corrupt your data is, you can recover the original data, whatever you're saying, by doing this particular task. Okay, YFM divided by HFM. This process, by the way, is called as equalization, right? This whole process is called as equalization. See the approach here. You are doing this in the frequency domain, right? You are doing this in the frequency domain, getting the original thing back from a corrupted channel by estimating the channel. That is what frequency domain equalization. Why? Because you did this entire stuff in the frequency domain, but there is a catch. Okay, so what actually happens now, we used I told you that since we are taking a FFT, we can do this whole stuff, but then wait a second, what actually happens in the channel is not circular convolution, but it is linear convolution. But DFT takes in circular convolution as, right, we have studied. That's the difference between a DTFT and a DFT. DFT is a convenient version of DTFT, which we are using because we wanted to use digital computers, right? Because we wanted to use digital computers. So what to do now? What to do now? So DFT considers circular convolution. What actually happens in the channel is linear convolution because the channel is linear. So what you have to do is, we have to fake the circular convolution by adding a specific type of redundancy called cyclic prefix onto the transmitted vector. Oh, what is that? Okay, so now let us see what are we talking about. So I hope you remember this particular classic problem of circular convolution, right? So you can see here, let me take this example. You remember this, suppose I take a data which is 1 2 3 4 5 6 in length, and I say I do a convolution with 1 2 1. Then you can see, say I take a 6-point convolution, circular convolution. So what's going to happen is, this here is an answer of linear convolution. But when I want to take a circular convolution, you can see, for an impulse response of length 3 of the channel, the last 2 bits of the linear convolution answer are going to come, last 2 numbers in linear convolution are going to come here. They are going to alias, and you will have this particular data. Now, is this data wrong, by the way? This data is not wrong. For first two values are wrong, but you can see 7 7 6 6. These 2 values are correct, right? These 2 values are correct, right? Here also you have an example. So now what I have to do is 2 things I know. First is, in circular convolution, depending on the length of the impulse response, if at all length of impulse response is m minus 1 number of values, last values are going to come and add in the beginning, spoiling the first m minus 1 values. Okay, they are going to get faded anyway. But I know, to be able to do the frequency domain equalization, I have to simulate, I have to fake a circular convolution impact. So what I will do is, in this particular data of 1 2 2 1 to 1, the last 2 bits of the actual data, I will append them in the beginning also. And now this particular addition is called as a cyclic prefix. Now, when I do this particular thing and I go ahead with the convolution, the linear convolution, so what's going to happen is, the initial data, whatever I have, is going to be the last 2 bits are anyway going to come and add in the beginning. Okay, they are going to come and add in the beginning. Am I interested in this particular data? No. Am I interested? No. But you can see here, my remaining answer matches that of a circular convolution. What I did here is linear convolution. You can see what I have done here is linear convolution. The answer I have got here in between, except for the first two bits, except for the first two values, the remaining answer, whatever I have, again, except for the last two values also, remaining answer what I have is same as that of circular convolution. Okay. So did I encounter any overhead here? Yes, unfortunately, because now instead of sending only 6 values, I had to send 2 values extra. There is an overhead, but then frequency domain equalization is a very handy tool to have and to recover my original data. So this is the concept of a cyclic prefix. So what is a cyclic prefix? Say you have some 6 or 8 bits, then 8 values, then if at all you take the last 2 to 3 values and append them in the prepend them in the beginning, such a thing is called as a cyclic prefix. Once you get the whole data done, so what you are supposed to is conveniently you remove those values. You remove those values. Okay, you need to do extra processing, but then it comes with the advantage. Okay, so nobody is complaining here. Okay, so that is the idea of a circular cyclic prefix. Okay, so here you can see if at all you have your OFDM data symbol, the last few values are taken and added in the beginning. And there is one more advantage also. You remember here we spoke about there is a likely chance of a delay spread, and few initial bits are likely, few initial values are likely to get overlapping with each other. So these cyclic prefix values, which are anyway going to be discarded, will now be will be affected. But still, since you are going to discard them anyway, you do not mind. Okay. Of course, it comes with a disadvantage because it adds to the overhead. Now, how do you choose? What value of cyclic prefix should I choose? Should this be 3, 5, 7, or 9? So this particular value should be determined by, first is the length of your channel response. How good you have estimated your channel impulse response. Okay. So the rule is m minus 1. If length of the channel impulse is say m, then m minus 1 values you need to take. Otherwise, it can also be decided based on your the guard bits, whatever you need based on your time delay spread. Okay, based on your time delay spread. So here is one example, by the way. So how? So you can see here in this particular example, minimum and maximum data rate loss due to use of a cyclic prefix. So here he has taken an example where he has linked the cyclic prefix based on the amount of time delay spread. So that's the usual case. The amount of cyclic prefix, whatever you need to put, how many symbols, how many values in the symbol you are going to use as cyclic prefix. It depends on the time delay spread in the channel, and also it depends on the standards. Okay, so you can see in this particular example how many values he has used. Okay, you can see at L equal to 128, the cyclic prefix length is 9. That means if at all the actual data symbol, say you are using a 128 point, okay, while okay, the rate, okay, so this particular numerical example, I'm going to continue here. You just read through this, okay. So now let us talk about the frequency equalization. This is what I was talking about. So once you perform the FFT, where here, okay, you took IDFT, converted data from parallel to serial, you added cyclic prefix HFN, some noise in the channel. So this is additive noise. That's why a plus n. Okay, you cannot avoid additive noise. Delete cyclic prefix, serial to parallel. You delete the cyclic prefix, but it doesn't matter. Your answer still matches that of a circular convolution. You do the DFT. Okay, so convolution becomes multiplication, and you do the frequency domain equalization. So that's the equalization we are talking about. So you have your data Y, then you know the channel, and data is in frequency domain Y divided by H. You get your original data. Fine. Okay, so that's frequency domain equalization, or in the block as they say FEQ, frequency equalization. Okay. So note that although FEQ inverts the channel, there is no problematic noise enhancements or coloring, since both the signal and the noise will have their powers directly scaled by factor 1 by h square. Okay. So let us agree. Let us agree with the author that he says, things are going to go fine. Okay, nothing can go wrong. So, okay. So that's typical OFDM for us. So I do not suggest this particular block diagram. I would suggest the earlier elaborate block diagram only. Okay, this is only for understanding. You can see the original data, whatever they are talking about, it is in frequency domain, and this particular channel, by the way, is in time domain. That is the whole reason why they took an IFFT at the transmitter and FFT at the receiver. Once again, let me tell you, let me advise you, do not use this particular figure as the block diagram, because there are so many confusing things here. They have not done the initial parallel to serial and serial to parallel and parallel to serial thing at the transmitter and receiver. They have used IDFT instead of IFFT. So both are sort of confusing, I would say, the previous diagram. But anyway, okay. So how does it work in OFDM in LTE? We will see this in next video. Let me stop here.